Welcome to Spring LIB.
Alrighty, so we got a basketball player, and he's diving or going for a slam dunk on the basketball hoop. And the way the problem describes it is from his center of mass. The center of mass of the player being at 1.02 meters, and it peaks at 1.85 meters, and it falls to 0.9 meters. Don't stress out too much about the word center of mass. That stuff's not going to come out till later, or come up until later in the textbook. And so, for that matter, don't stress too much about it. You can just picture this as some sort of particle that projects via the projectile motion pattern up to here. It peaks, and then it following a projectile motion pattern, falls back down. Just a little bit more on the lower end of the motion. So the way I like to break this down into two motions, you have an upward motion and a downward motion. Doing the upward motion first, we'll go ahead and use this equation here. Vy final equals Vy initial squared plus 2ay. That's the acceleration in the y direction, and then you can just put a delta y here, okay? Now the velocity at the end of the motion, right here, upward motions here to here, at the top, the velocity is completely going in the horizontal direction, and because of that, this part is going to be 0. So we'll go ahead and put that there as 0. It's Vy initial squared, we don't know, so let's put Vy initial squared plus 2a delta y, and we're going to actually go ahead and put a minus right away in front. How come? Because we have gravity being negative, so it's a negative g here. The negative will end up coming out in front ultimately, so I'm going to put a negative there right away. 2g. The acceleration is g. It's a negative 9.81. That's why the negative's here. And the delta y is 1.85 minus 1.02. Delta y is final minus initial. Cool. And you can go ahead and you can solve this for the Vy initial. And that'll equal 2 times 9.8. I remember when I brought this over to the side, you end up clearing the negatives. That's why there's no negatives left here. And then the 1.85 minus the 1.02, you do that, you get 0.83. I'll just extend this root all the way out to here. And then Vy initial, go ahead and punch that in. You're looking at 4.03 meters per second. Cool, awesome. Now we're going to look at the downward part of the motion. I'll do that up here. Let's write downward. Okay. So for the downward part of the motion, we're going to use the same equation that we just used, with just a few modifications here. Okay, excellent. So when we do this, let's see here. So the Vy final at the beginning, you're going to have, well, at the end here, this final, you're actually going to have a velocity here. So that's going to stay put. So Vy final squared. Now the Vy initially, remember, you're analyzing motion downward, so it's from here to here. And there is no initial anything in the y direction because it's all going horizontally, similar as to why there was no final velocity in part 1 here, or for the upward motion that we were analyzing a second ago. So we can go ahead and put 0 in for that. Very convenient. And then we're going to have our minus number, same reason, because of the gravity again. Negative 2 times the 9.81. Which has a negative next to it, but it's moved out in front. That's why that's there. And then we have the delta y. Remember, delta y is final minus initial, so 0.9 minus 1.85. So we're going to do that 0.9 minus 1.85. We're getting negative 0.95, negative 0.95. Okay, excellent. So we have two negatives here. The negatives come out front, and we can actually, this cancel becomes a positive, and we take a root of both sides. Just a lovely thing to do. Excellent. So V, just giving myself some space here so stuff doesn't get mixed up. Vy final equals, after you go through that math, you get negative 4.32 meters per second. Excellent, cool. Of course, the negatives went away inside the root. Why did I bring the negative back? Well, mathematically speaking, how it was working before with the gravity pointing in the same direction of motion for that latter part, we'll actually have to bring the negative back into the problem, because if you look at our diagram here, when the object is landing, it will be pointing in a downward direction and a negative direction. So it's going to be alongside the same direction as gravity, which was already interpreted as negative in this problem. Excellent. So now we can go ahead and find the time of flight, which was the original big goal of this first part of the problem here. So we'll go ahead and do that now. We can go ahead and use this equation. This box is away here, so we have some space, and we have Vy final equals Vy initial plus acceleration in the y direction times time. Now, of course, we can go ahead and put our information in that we know, which is negative 4.32, which we just found, equals 4.03, which we had found earlier, minus y minus, because it's a negative g, minus the 9.8, 1 times t. And you can go ahead and move everything over to one side and completely isolate this guy, and then isolate t further, and you can go ahead and you can get a time of flight of 0.852 seconds by isolating t and solving. That's our time of flight. Box that in right here. Excellent. Cool. So now we want to figure out the initial horizontal velocity. So let me go ahead and I'll do that over here. I'll put this equation down. We have x equals x initial. And now, one thing I do want to mention about this, just to save some time here and to make sure this is clear. The question is asking for the initial horizontal velocity. Remember, this is a projectile motion problem, and because of that, the horizontal velocity is going to not be affected by any sort of acceleration. And because of that, the last part in this equation is going to go away. I'm going to show you guys real quick exactly what I mean, though, just so this is clear. Vxi t, this is what you're essentially trying to solve for, is velocity initial in the x direction. And you have plus 1/2 acceleration in the x direction times t squared. The acceleration in the x direction does not exist. There is no acceleration in the x direction. So that goes to 0. So that last part you don't even worry about. It doesn't exist. X minus x initial. We can go ahead and just plug in what we know here. We know that the x final, if I go ahead and just label this here, we know the x final, where it ends, is equal to 2.8 meters. Okay, and we also know the t from when we found it a minute ago there. So with that in mind, this is simply, in the x initial, you can set as equal to 0, so this goes away as well. So you have 2.8 equals this VXI times T, and T is 0.852. Of course, this 2.8, by the way, is given in the problem. And we can go ahead now and you can divide this guy over. And then when you do that, you'll get a value for your initial velocity in the x direction. And that is equal to 3.29. 3.29 meters per second. Excellent. And now for the next part, we're going to want to find out the velocity in the y direction. So we can go back to that's actually the easiest one, because that one we actually have right here. We had already found that earlier, naturally, in our problem solving process. We have both of those components, and then we also want to find the takeoff angle. So using the theta trick from trigonometry, or the tangent trick, you have v y initial on the top, or your y component on the top divided by your x component down here. And close that down, and then go ahead, plug in what you know. It's 4.03 divided by the 3.29. Take the inverse tangent, and you're looking at 50.8 degrees. Cool. There's your takeoff angle. Awesome. Okay. So now the next part of the question is asking us something a little bit different this time around. So we have a different object doing this motion. And in that case, there's just a few adjustments we have to make to our diagram over here, which I'm going to do real quick. I'm just going to erase the original numbers we have here. And I'm going to fill in some new numbers. And then we're going to work with those numbers and get some new answers. And I'm going to try to do that in this space down here. Fortunately, though, since we've already done all the really hard, grueling work for this, this latter part won't be too difficult. So let's just go ahead and fill in what we know real quick. So we know that the initial is 1.2 meters, so we'll put that right here. 1.20 meters. And you've got your 2.5 meters for your max, 2.5. And then we got 0.70 for our lower end there, 0.7 meters. All right, so let's do the same procedure again. We're going to break the flight down into two parts for the time of flight. We'll do the upward and the downward. Fortunately, though, you can take a little bit of a shortcut and just run right to this equation first, instead of going through the same stuff you did here. This is the same kind of problem again. It's just the numbers are changing. So we're going to use that same equation here that I just pointed to. We'll just do that right here. So the Vy initial, and that's going to be equal to square root, and you have the 2 times the 9.8. And you have multiplied by the delta y. Remember, this is that 1.85 minus 1.02 that we had before. This time it's 2.5 minus 1.2, the final minus initial for that, that upward motion. So if we do 2.50 minus 1.2, we'd expect to get 1.3. So we'll go ahead and we'll plug that right into here. Still following from underneath our root, you can go ahead and you get 5.04 meters per second. Excellent. And we'll do the same with the downward part. We'll do that right here. Same kind of deal again. We can kind of take that little step and jump right to this area here. So Vy final. And that's going to be equal to 2 times number 9.81. So I'm just going to put G there. And you have the same, now the delta Y for that lower part of the motion, which is that before, if you remember, it was a 0.7 minus 2.5, and then the negatives go away. 0.7 minus 2.5, it's negative 1.8. And you have a negative here with the G, so negative G and negative 1.8. The negative goes away, you're just left with 1.8. underneath that root. Close this down, and then you get a V final in the Y direction, which actually just in the effort of space, I'm going to place that to the right of what we just did here. And that's going to be negative 5.94 meters per second. Excellent. Now with that, we can go ahead and apply the last formula we did last time, which was not too bad. So let's go ahead and do that. Actually, this time around, we'll use this guy. Let me show you guys this equation real quick. Final. I'm sure you guys have seen this before. That's plus the acceleration in the Y times time. Of course, you guys have seen this before. We did this right here. It's the same equation. So same deal. Go ahead, plug in what we just found from a moment ago. We have the minus 5.94. And if we set that equal to the 5.04, which we found right here, 5.04. And you have this multiplied by, or you have the addition then. You have the acceleration, the 9.8. But of course, remember, it has to be a negative 9.8. Times t. And once we clear this all up and we go through the math, we get t equals 1.12 seconds. Box this guy in right here. Lovely. And that's the time of flight for the slightly different situation that we got going on in the second case scenario.